Accuracy assessment. This is a crucial topic and necessary for every classification, I would say. A quick definition here, accuracy assessment methods can produce statistical outputs to check the quality of the classification results. And actually it doesn't matter how you classify your image objects, if you use supervised classification, unsupervised, knowledge-based, deep learning, template matching, whatever. It doesn't matter, you can use this approach to check the quality of your classified objects. And this is an important part of any classification project. It compares your classified objects with validation, ground truth data. So you need two things. You need classified image objects and somehow ground truth data. In our example, we're going to have ground truth data as a vector file, but it also can be a raster, or you can manually create it in eCognition or whatever. And this is usually what you get when you do an accuracy assessment, such a confusion matrix, or also called error matrix. And this gives you detailed information about your single classified objects compared to your ground truth data. You get the producer's accuracy, the user's accuracy, and all sorts of statistics that help understand the accuracy of your classification. So what do you need to get such a confusion matrix? First of all, you need classified image objects, and then second, you need validation data as samples or object variables. So somehow you need to convert your ground truth data that you have maybe as a vector into samples or into an object variable, and then you can create this confusion matrix easily. Which algorithms are we going to use? As stated before, we're going to have a vector file as representing our ground truth data. So we're going to convert thematic objects to samples because we need samples or object variables to do the accuracy assessment. And then we have an algorithm called export confusion matrix. This one exports your confusion matrix as a CSV file, and then you can open that one. And we also have an algorithm called compute accuracy values. This one allows you to compute the overall accuracy and Cohen's kappa and store those two values into separate variables. And then you can use those variables within the rule set as a stopping criteria or as a looping criteria or whatever you like. Let me quickly show you how that looks like. So this is an algorithm, compute accuracy values. And yeah, what you have to do is choose the right level in the domain. I have multiple levels here, so I'm gonna go for level 1. So it's using the samples there. If I choose here input data, image object level, class filter all, ground truth. In my case, I have samples as ground truth and Cohen's kappa. Save this in Cohen's kappa variable. This create variable dialog pops up, hit OK. Same for overall accuracy. Hit OK and execute. And there you have, in the object information window, you get these values and you can use those again in the rule set as thresholds, as whatever you like. Finally, we also have an accuracy assessment tool within eCognition, which allows you to display the confusion matrix within eCognition, and you also can export the confusion matrix using this tool. And actually the previous screenshot that you saw regarding confusion matrix was taken from eCognition, so it looks like the screenshot before. Here are the workflows that I want to show you in this tutorial. First one is accuracy assessment based on point vector, object based. Second one is same, but pixel based. And for those two examples, I'm gonna use samples, and actually also for number 4, 5, and 6. So only number 3 is using object variables. And what are samples? Actually, samples can be displayed in eCognition on an image object level. So you can have different samples actually on different image object levels. That's something new. You also can copy those. If you do a copy level to one above, you can copy the samples, yes or no. And you can have different samples on different levels. So for example, on level 1, you can have samples to do a supervised classification. That's how traditionally samples are used as input for training data. And on another level, you can have samples for validating your classification, right? So validation data. And some helpful features, for example, are, I'm gonna simply show it here quickly in the object information window. So you can display actually the number of samples per level. I do have here 2 levels, and one level has here 10,000 soil samples, and this level 2 has 21. So I could use, for example, level 1 to create a supervised classification, train the model and apply it. And then on level 2 I can do a validation and an accuracy assessment. And I also display here the total number of samples. Number 3 is then using an object variable instead of a sample to do an accuracy assessment. And using object variables instead of samples might come in handy if you, for example, already have samples for supervised classification or something, right? Traditionally, if you do a supervised classification, you train the model based on samples that you have. And then if you do a validation and you don't want to override those samples, you can use object variables instead. So you have your samples for training the model and then your object variables for validating your model. Then number 4, accuracy assessment based on a polygon vector. So if you have a polygon instead of a point, how does that look like? It's exactly the same, but I'm still going to show you that, and also going to show you object-based and pixel-based. And then number 6, accuracy assessment based on point vector, object-based, but workspace. What does that mean? I'm going to show you how you can apply this across a whole workspace. Imagine you have like 100 tiles and you want to do an accuracy assessment on all tiles and have the accuracy measures for each tile separately, but also the overall accuracy combining all the tiles. That's now possible in eCognition. We have this option in the export confusion matrix algorithm called flattened error matrix. So you can export a flattened, and if you apply the flattened on workspace, it as a result combines all flattened into one CSV file, and then you can load it in eCognition and display it and also export it as a standard confusion matrix. Sounds complicated, it's not, and it's a very nice tool to get accuracies across workspaces and also see which tile has issues maybe in the accuracy. All right, I think that's it. Enough talking, let's have a look at the first workflow. Let's open eCognition and choose open workspace, because I saved the workspace for you that you simply can open. In the data folder AA workspace, you should have this dpj file. Click open and you instantly gonna have the data set and the rule set in there. I'm gonna go to the data management layout and I see that there's one project. Simply double click it, it will open, and then I'm gonna change to the rule set development layout. And here the rule set, it's numbered based on the different workflows that you saw a minute ago. 6 different workflows. This setup and reset section simply creates image objects, classified image objects based on a vector that I've loaded called classification here. That's because you need classified image objects, right? So that's not really a part of the accuracy assessment workflow. That's simply what you need to do an accuracy assessment. You need something classified, right? So the input vector, quickly going to display for the classification, is this one. And I simply use this and the information of the vector to classify my image objects, and they are all classified. I'm gonna quickly change the outline color because I prefer black. And yeah, let's have a look at the first workflow based on point vector. So it's very simple. It's just 2 processes. First of all, as stated before, we need to convert our ground truth data that actually we have here as validation as points. And yeah, what we're going to do here is we convert them to samples, and then the advantage of samples is that you can display them in eCognition, and then we use the export confusion matrix. So a 2-step procedure, and then you have your accuracy assessment. how does my ground truth data look like in this case? You see here the vector layers. I do have one called validation points. Those are simply points. And I have another one, validation polygons. Those are validation polygons that we also can use. But first I'm going to use the points, and I'm going to open the first one, convert thematic objects to samples. Again, this converts thematic objects to samples, so a vector information to samples. And what you have to do here is select the thematic layer here, then select the column where the classification is stored in the attribute table of the vector here. And then you have the option to choose match class names. It can happen that the class naming of your vector of your ground truth is different to the mapped values here in the class hierarchy in eCognition. And this interface simply allows you to connect those, right? If you have different languages, let me jump in here real quick. This is an example of matching the class names. So on the left-hand side, you see the class names in the attribute table that I want to use, and on the right-hand side, the mapped values, so the values in my project. I have German names on the right in the project, but English in the vector. And you simply can map those, they are connected, and then it's gonna work just fine. Talking about this remapping, I also want to quickly show you this new algorithm here, update map thematic attribute. This one does more or less the same. You can map values, right? So you can create a new column in the attribute table, and there you can remap the entries in your column of the thematic layer to the classes in your project. And here in this interface, you also can uncheck here in the bottom left this map to class, and then you can map it to any value. You can enter then in the mapped value column on the right anything you like instead of simply classes. All right, sorry for interrupting, and now we're gonna continue with the original video. See ya. Whatever, different naming. You can make this connection here and remap those attribute values so they know which class they should represent here in eCognition. In my case, this is not an issue. It's all the same, the naming is the same. And then we have the overlap requirement parameter. This one actually doesn't apply if you have points, only if you have polygons. I'm going to talk about this in the polygon section later. Actually, for point vector, samples are only created if all points within an image object are of the same class. Otherwise, it won't be used. Right? I think that's it. Let's execute this one. And I'm going to display the samples here at the bottom, so you see how they look like. So actually, every object that overlaps with a validation point is classified as a sample. See here, that's a forest sample, and the classification is also forest. So that would be a good classification in that case. What else? This object here is a low vegetation sample, and it's also classified as low vegetation. So this at the bottom displays my ground truth information. And yeah, how to display samples, you actually change the fill here from class to samples, and then you get the samples. If you set it to class, you get a classification. And that's a good thing about, or an advantage of using samples, because you can display them and you see which objects are samples, right? And how they look like. So, is this already an accuracy assessment? Almost. We can now compare our classified objects with the samples. And first of all, I'm going to show you the tool under Tools, Accuracy Assessment. And you have different statistic types, confusion matrix based on flattened file, that comes into play when we apply accuracy assessment on the whole workspace. Confusion matrix based on samples and object variable, and we are interested now in confusion matrix based on samples. You can define the level here, And that's actually it. And now you can click show statistics and you're gonna get an accuracy assessment. So you're gonna get a confusion matrix based on the samples. Right, all the statistics here, and you also get a nice heat map. Yeah, but most of the time you want to export it, right? And therefore we have this export confusion matrix algorithm where you simply can export a confusion matrix based on image object level or flattening confusion matrix. So we want to do it on as input data is our image object level. You can set a class filter here, ground truth, sample class, object variable. In our case, we have samples. Add detailed statistics to export. If you set this to no, let's set it to no first and then set it to yes afterwards, so you see the difference. And yeah, if you execute this, it's gonna create a CSV file in this default directory. So in this workspace directory, it's gonna create a results folder. There you're gonna find this, a subfolder called number 1, which represents our first workflow. And in there, you're gonna have the confusion matrix. Open that one. There you go. This one is very simple, no detailed statistics. If we change this add detailed statistics to export to yes, execute again, have a look at the file, you see that we have those detailed statistics that are actually fairly interesting. All right, now the question is, if you want to have this pixel based, so if you don't want to compare the objects but simply the classification exactly at the point of your ground truth data, of your validation, I simply want to show you my workflow, how I would do it. First of all, I'm going to run the setup and reset section, so we have clean classification and no samples. And yeah, what I'm doing here is in this number 2, if you want to do it pixel based, I do a vector based segmentation on the image object level using my validation points. And what this will do is create pixel based or pixel sized objects where you have a point, right? And if you then run the convert thematic objects to samples, the samples will only be a pixel, right? A single pixel, which is the smallest object that you can create, and you don't have those objects anymore, right? And then you can run again the export confusion matrix. It's the same as before, nothing has changed. Have a look at the results folder number 2, and there you have it. Slightly different results, I would guess. All right, hold on. Why could this actually happen? The reason for this is that for point vectors, samples are only created if all points within an image object are of the same class. So you might have less samples for validation if you use the object-based approach, in this case compared to the pixel-based. And you also, again, you can use this accuracy assessment tool based on samples, show statistics, and get it right away in eCognition. All right, I'm gonna reset everything, and then we're gonna have a look at number 3 using object variables. So you can compare your classification against samples or against object variables. And my workflow was here to convert the information from our vector attribute table into an object variable using read thematic attribute that reads information from the attribute table of my validation points vector and uses this column, and it's going to write that information into an object variable. I'm simply going to create a new one here because the settings are crucial. A new example variable. So if you create that object variable, you first have to change here from scene value to object value, because it's not a global value, it is for each object differently, or it should be. And you have to change it from double to string, because you enter string information, you enter text, right? Hit OK, and then you can use it here. but I'm gonna use this val, which stands for validation variable that I created previously already. Hit execute, and now we don't have samples, but you see here in the object information that this object has this object variable forest, which corresponds to our validation points, right? The other object here has the value of 0, all 0. So we have to look and find objects that overlap with validation points, and they should have the information here as an object variable, right? So taken from the attribute table, written into an object variable, and then we can here, instead of using the export confusion matrix function, instead of sample class, we can use object variable. You have to choose the variable that you want to use, add detailed statistics to export, execute, and let's have a look at our number 3. Looks like this. And also object variables using the tool here, accuracy assessment. Based on object variable, choose the variable and then select the classes, show statistics. Here we go, same thing. I'm gonna reset quickly. Number 4 now, let's assume you don't have a point vector, you have a polygon vector as ground truth. Same workflow, it's exactly the same steps, I didn't change anything actually. First, convert thematic objects to samples. So again, we need samples or object variables, so I'm gonna go for samples here. Now I'm gonna choose my validation polygons instead of the points. This is the column and attribute table. You can match class names if you need to. And then you have 2 more options here that you don't have for the points. Class with max overlap or class with max overlap and threshold. So that simply defines how the overlap is handled. And yeah, select how class for image object overlapping with thematic object is selected. If overlap requirements is not met or class is unclassified, sample will not be created. Right, so if you go for class with max overlap, it's gonna classify quite a few objects. I'm simply gonna show it. Execute this, and I'm also gonna display the validation polygons because we're using those now. And you see all objects that are overlapping, also if they're simply overlapping slightly, those are used as samples using this setting. And that's maybe not something that you want to have actually. So what you could do is, instead of class with max overlap, go to class with max overlap and threshold. Actually, default value is set to 50. That means that an object has to overlap with 50% or higher with the polygon. All right, I quickly gonna delete the samples. Gonna quickly add a process, delete samples. That's simply gonna delete the samples, right? I'm gonna put it at the bottom. And now I'm gonna execute this convert thematic objects again. And you see we have way less samples now because it only used those objects that are overlapping with more than 50%. Right, now let's go to 75 and we should get even less, right? If you go to 100, you only will get those that, hold on, first have to delete the samples. You only will get those that are 100% enclosed by the polygon outline. And what you also could do is using a vector-based segmentation and cutting out those polygons so you only get samples exactly within the boundaries of your polygons. And I am quickly going to show you that. I'm going to add a new process here and I'm looking for the vector-based segmentation algorithm. And then change pixel level to image object level because we already have image objects. You can leave this default thematic layers. It's gonna be our validation polygons. Okay, and level is correct. Execute, and that has to happen before the convert thematic objects to samples. And if we now look at the object outlines, gonna undisplay. So the objects are now cut along the outlines of the vector, right? Now execute this one, the convert thematic objects to samples, and then you're gonna have a different result. Let's display it down here, right? Only, and display the polygons maybe. Yeah, and now it's limited, right? It's cut exactly at the outline of the polygon. Therefore, we do have different samples here compared to the previous approach. The previous approach without this vector-based segmentation can create object samples that are actually outside of your validation polygons. Here, this is not the case. Now I'm quickly gonna clean up the rule set because I want to focus on this workflow that is implemented already in the rule set, so without this vector-based segmentation. I simply rerun the setup section and remove this vector-based segmentation from the rule set. Back to the original example here in the rule set, what we're gonna go with is the max overlap setting, and run that and create the accuracy assessment. So in the parameters, overlap requirement, change this to the max overlap, execute. So we have quite a few objects, and then we can export, exactly same as before, nothing else. But let's first have a look here at the accuracy assessment. Samples, show statistics, right? And you see the number is way higher now and way lower accuracy. That makes sense because you have this huge overlap. Let's try to increase the accuracy. Overall it was 0.46. I'm going to delete the samples, and you're going to see the impact of the overlap. If we go to 50, we should have actually higher accuracy now. Tools, accuracy assessment, samples. Yeah, 0.57. That's a way how to increase your accuracy, right? Well, and export, I executed that already. Same as before, you get this CSV file with all these statistics. Good. How would it look like if you want to do a pixel-based, but you have a polygon as input? Same workflow, I mentioned it just briefly. You can do vector-based segmentation. That's what I mentioned previously, to cut out the outlines of the polygon. But if you want to do it pixel-based, you can apply a chessboard segmentation, right? On the image object level, but only on areas where you have an overlap with the polygon. So it's gonna do a chessboard segmentation on all objects that are overlapping with the polygon. I'm going to choose object size of 1, which means it's a pixel size, and then you can do the accuracy assessment based on those objects. So first, chessboard, and you see if the object overlaps with my polygon. I have now pixel sized objects. Now I use the convert thematic objects to samples, and then the samples only going to be within my polygon, and I'm going to have tens of thousands of validation points, more or less, because now it's pixel based and the input was or is a polygon. Here we go. So you see the samples at the bottom, and you see that this stuff here is gonna be flagged as misclassified, right? Because the sample says this is low vegetation, but here this is bare soil, but this is only low vegetation, and that's gonna be the case in quite a few areas. Let's go here. Right. Validation data says this is forest, but the classification says only this area is forest, and we have some urban areas or man-made, low vegetation and bare ground. Right. Let's export the confusion matrix and quickly display number 5. Yeah, you see 18,000 forest, and so on. So way more validation points. And again, accuracy assessment tool here, you get exactly the same as the export. It's no difference. All right. Now the interesting stuff. I mentioned it previously, number 6 here. If you want to do an accuracy assessment across a workspace, having multiple projects, you can use the so-called flatten confusion matrix option here. If you use this one, it's gonna export a confusion matrix and not in a standard format. It's called a flattened format. And afterwards, eCognition automatically, if you run that in a batch process, it's going to create automatically one CSV file combining all flattened from each project that you've processed in the workspace, and then you can display the confusion matrix across the whole workspace, but also for each single tile or project, right? So let's have a look at this. What I'm going to do is I first have to create somehow tiles. So I'm gonna delete this level here. So we have a clean project, and then I'm going to create tiles. So I'm gonna switch to the data management layout, right click on my project and choose create tiles. And I'm gonna go for maybe 400 times 400. Let's see how many tiles that will create. All right, 16 tiles, and let's have a look at each single tile here. Right. Now what we want to do is get an accuracy assessment across all tiles and also for each single tile, right? And again, the workflow is exactly the same. What you simply have to change is this flatten confusion matrix, set this to yes. And I'm prepared a rule set for you. So what I'm going to do is I'm quickly gonna load this rule set that I've prepared for you, which is called rule set AA workspace batch processing. And I'm going to delete the rest. All right. So what this one does is I'm simply going to execute here quickly on this tile. It classifies the image objects. Then it uses the validation points, and yeah, it creates samples, and then it exports the confusion matrix using this flatten confusion matrix setting set to yes. And if you do not have a server license, you actually have to watch now. Otherwise, you can also apply it on your tiles. So you need a server license to do batch and parallel processing in eCognition. I still need to activate my server. I'm going to Tools, Manage Local Servers, Enable. I do have 4 engines. And now I'm ready to go. I'm going to select all tiles, right-click Analyze. And now I have to choose the rule set here, this batch processing rule set, and save with rule set. Yeah, why not? And start processing. Now it's going to process each tile, right? It's going to export the confusion matrix. I'm going to show you that in a second. Yeah, and then we're going to try to create a regular confusion matrix based on the exported flattened one, right? So now all tiles are already processed. Let's have a look at the workspace. So we have this new folder confusion matrix, and this holds the flattened confusion matrix for each tile, right? But more interesting is this confusion matrix out here, which is a combination of all the tiles. Each line here represents the results of a tile so it's a flattened confusion matrix for a tile. And yeah, as you see here, we have 16, and this represents our 16 tiles. That looks very cryptic. How can you get this to look nice and like a regular confusion matrix? You have 2 options actually. First is using our tool here, the accuracy assessment tool, and choose confusion matrix based on flattened file. Now load file name, we have to navigate to this flattened confusion matrix that was exported. So in our workspace results, this one out here. So that's the combination of all those. But first I'm going to load a flattened confusion matrix of a single tile. Let's have a look at the confusion matrix here. We have an overall accuracy of 1. The reason being is that we probably have just a few points there, but more interesting would be the combination. So how accurate is our workspace, more or less? All projects in our workspace, all tiles. And I'm gonna load this confusion matrix show statistics, and that is the result. So it looks like a regular confusion matrix. What you could do is you could save, click the save button here and save it in the workspace or anywhere else, and this would actually export the confusion matrix directly here, more or less manually. But you also can do it from within the rule set, right? Let's have a look at this one here. Export confusion matrix. This parameter here, input data, if you change that to flattened confusion matrix, you also can convert a flattened confusion matrix into a regular one and simply load here in the input path the combined flattened error matrix that we exported, add detailed statistics, set it to yes, and execute. And this will create confusion matrix aggregated. This will create also the same confusion matrix. So 2 different ways to get the confusion matrix based on a flattened confusion matrix. All right, so that's it. Mainly the takeaway should be it's very easy and you can implement it in your rule set using the export confusion matrix algorithm, and you can compare your classification against samples or object variables. And I showed you how to create samples. You also can use the samples tool to create samples manually and then do an accuracy assessment. That's also possible. Or you can create object variables and do the accuracy assessment based on the object variables. So if you don't have a thematic layer or a raster with ground truth data, you can do it also manually in eCognition. Easy. And yeah, this new algorithm, convert thematic objects to samples, is very nice because you also can map the different names of your vector compared to your class hierarchy right in eCognition. And what I didn't show you is the compute accuracy values algorithm, but that's very simple. You can execute this one and it writes the overall accuracy and Cohen's kappa into variables, and then you can use those as thresholds or whatever in your rule set. And I think you also saw the advantage of the accuracy assessment tool, so you instantly can see the confusion matrix within eCognition yourself. And yeah, the workflows were different, object-based, pixel-based, and I also showed you object variables. And what I really like is this the functionality now that you can apply or compute the accuracy across a whole workspace, right? Using this flattened option, and then it applies it on all the tiles that you're analyzing, and afterwards you have this combined CSV file with all the flattened outputs, and then you can convert this into a regular confusion matrix. So that's very neat. Now I'm gonna stop. Thank you very much for watching. If you have questions or concerns, have a look at our knowledge base or into our community, post a question, and yeah, see you there. Have a great day. Goodbye.